Hi everyone, welcome back to Rocks for Jocks. As I mentioned in my prior episode, the book The Theory of Everything by Stephen Hawking is a pretty short book. I originally intended for the whole summary and review of the book to be one episode only before I started reading it. As I started getting through the first couple chapters, I was happy to take my time with them because I figured that's where the hard stuff was going to be and it might get easier from there. It turns out the latter chapters get even crazier. So the review of this book will definitely spill over into a third episode, just so everyone knows in advance. As a result, I'm going to try to keep things as light and entertaining as possible as we go along. I hope people are enjoying this. Let me know what you think. In lecture number 3, Hawking dives into some of the details about black holes. They were only named black holes recently in 1969. At the time, scientists were split on whether light was composed of particles or waves. And later on, we know that both views are actually correct in their own ways. But the reason this was important at the time was that if light were made of particles, scientists thought that their reaction to black holes would be the same as any other particles. Light particles would be unable to escape the dying star's gravitational pull. Next, Hawking goes on to talk a little bit more details about stars' life cycles and how black holes form in general. The basic life cycle of a star and its death goes something a little bit like this. Number 1, a star is formed when gas, mostly hydrogen, starts collapsing due to gravity. Number 2, as the hydrogen is collapsing, the hydrogen atoms start colliding more frequently, which causes the gas to heat up. Then the atoms move faster and its atoms collide more frequently even more. Number 3, that feedback cycle, which causes the hydrogen atoms to collide more frequently and faster, sometimes causes the hydrogen atoms to merge and form helium. Energy released from this process is what gives most stars their well-known heat and light. That process also increases outward pressure, which continues to increase until it balances out the gravitational attraction pulling gas inwards, and it stops the gas's collapse. At this stage, hydrogen continues forming helium, where energy is slowly released to continue keeping that gas cloud around the same temperature and pressure, resisting collapse and staying around the same size. Counterintuitively, heavier stars actually need more fuel to balance out heavier gravitational pulls, meaning that they run out of fuel faster than smaller stars. This then results in heavier stars cooling and collapsing faster than smaller ones. In 1928, an Indian graduate student, Chandrasekhar, found that when large stars collapse, they can only actually collapse to a certain size. This is going to be because of something called the Pauli exclusion principle, which tells us that two pieces of matter cannot have the same position and velocity at the same time. This principle stops the gravitational collapse because in many stars, the distance between hydrogen atoms and their electrons can only be compressed so far. These small compressed stars are going to be called white dwarfs. Chandrasekhar also found that some stars would actually have enough mass and thus enough gravity to overcome the strength of the Pauli exclusion principle during their collapse. These stars would have to be around 1.5 times the mass of our own sun. However, some of these large stars can still be supported by the Pauli exclusion principle at the proton and neutron level instead of using hydrogen atoms. In other words, the protons and neutrons can still only be compressed so far. These are then going to be called neutron stars. Chandrasekhar then takes this even further to imagine what would happen with even more massive stars, whose gravity could theoretically overcome the Pauli exclusion principle amongst protons and neutrons. These stars, Chandrasekhar thought, could collapse to being infinitesimally small. He also said that a collapse to being infinitely small could even happen with neutron stars, which eventually run out of fuel. Now, this is not a very popular view at the time. Most researchers, including Chandrasekhar's former advisor, Albert Einstein, and a bunch of others, thought that a collapse to infinite density was not possible. So Chandrasekhar eventually gave up this line of research, but he did receive a Nobel Prize in 1983, which was partially due to this work. The next major breakthroughs in this line of research didn't come until 1939 from Robert Oppenheimer. Pop culture reference here. As many of us know, he was soon pulled into the atomic bomb research during World War II, so he did not continue too much further with his research on dying stars. Later on, after some projects by Roger Penrose and Stephen Hawking himself, Penrose proposed the cosmic censorship hypothesis, which is saying that singularities could only be found in hidden places, like black holes or the Big Bang. The reason that these are considered hidden is that a singularity in a black hole would cause our laws of space-time to break down. So it would look like the end of time for anyone reaching it, similar to the Big Bang being the, quote, beginning of time. In 1967, a researcher called Werner Israel said that any black hole not rotating must be perfectly round or a spheroid. A spheroid is just a shape that's like a ball with a bulge around its middle. So, for example, the sun is technically a spheroid with a bulge around the middle of it. Additionally, Israel found that black holes can be rotating, but they cannot be pulsating. This leads to one of two possibilities. Either all non-spherical black holes eventually collapse, or all black holes act as fluids and only form sphere-like shapes in the first place. A series of projects, including some by Hawking, later showed that during a gravitational collapse, the second possibility is what will always happen, which is saying that a sun collapsing into a black hole will always be a rotating spherical shape. In fact, its mass and rate of rotation will be pretty much the only information that we can determine about a black hole after its collapse. In other words, most of the information about that star before its collapse gets lost due to forming a black hole. For a really long time, the scientific community accepted black holes mathematically without any direct observations of them. Quick note from my own opinion. I would classify theories that are widely accepted by the scientific community without direct observations as actually pretty rare. This only became common in the early 1900s when theoretical physics was taking leaps and bounds while experimental physics chugged along at a steady pace. This continued until the late 1900s when experimental physics started catching up. So in the last 50 years or so, we've made a ton of technological progress and provided a lot of research evidence of former theories. But in the meantime, we've made much less progress on theoretical physics. This is seen most clearly with big projects like CERN, where we spend a lot of energy and money putting together these giant projects to provide evidence for or against theories that we've already had. But scientists are no longer necessarily putting forward new groundbreaking theories every year. And that's okay. It's okay to switch back and forth between, I guess you might call it theoretical and practical applications of some topics like physics every now and then. This chapter finishes up with the clarification that while light and almost all other particles cannot actually escape black holes, these black holes do glow with a small amount of radiation. Counterintuitively again, smaller black holes actually glow more. So we may be able to find smaller black holes more often than larger ones. Lecture number 4 starts with how Hawking and Penrose define a black hole. They decide that it is going to be the location where light just fails to escape. And they call that edge of the black hole the, quote, event horizon, unquote. The next interesting tidbit Stephen Hawking gives relates to entropy, which is the property of things becoming more chaotic with time. The classic example of this that I would always get in middle school and high school is that at the end of a school week or a work week, most people's bedrooms would be much messier than they had been at the beginning of the week. This property holds true for almost everywhere in the universe, where things get more chaotic and messy over time. The reason I'm bringing up entropy at all is that Hawking suggests we could theoretically violate laws of entropy by throwing an item with high entropy, such as a box of gas, into a black hole, effectively reducing the sum of entropy in our own universe outside the black hole and increasing entropy within the black hole. But because we get a decrease on one side and an increase within the black hole, the total sum of entropy in the universe still remains the same. A Princeton researcher then suggested a way to measure entropy within a black hole by measuring the area of its event horizon. Next up, I have a note from myself about what the area of an event horizon means. So if we're looking at a baseball, for example, if we ripped off the leather from a baseball and flattened it perfectly on the ground, we could then measure the two-dimensional area taken up by the leather of that baseball. And that would be the baseball's surface area. So similarly, the surface area is, we can think of as like the cover of the black hole, like the what wraps around it. Back to the text. As a black hole's event horizon expands and more mass is unable to escape its gravitational attraction, the black hole starts emitting particles at exactly the correct rate to prevent violations of entropy. So this was a pretty confusing section, and again, I had to read it several times. So Hawking goes on next to explain how it's possible that some particles are able to escape. The background on this is that what I normally think of as empty space actually does have some gravity and electromagnetic fields existing there. Therefore, we can think of mathematical values in those fields being slightly different than exactly zero. So there's not really going to be any space with zero gravity or a zero electromagnetic field, because we know that those fields do exist everywhere. That means that position or velocity of any types of particles are always going to be slightly different from zero at any point in space. And this small uncertainty we can call quantum fluctuation. We can think of these fluctuations as a pair of virtual particles which move apart and then destroy each other when they come back together again. These virtual particles cannot be directly observed, but can be indirectly observed, such as changing electron orbits, for example. Now, due to the conservation of energy, each pairing has one negative and one positive particle. The positive particle is going to be the one which has a small chance to escape the black hole as a real particle. To a certain extent, I think it's okay for me to admit that I don't understand some of these concepts without fully digging into the math behind them. It's kind of mind-blowing stuff, so if we don't talk through the math in detail, I don't know if the concepts are going to make perfect sense. I definitely think that we should try to understand them as much as we can and talk about them, try to understand the implications and why people are still researching them. But I think it's also okay to admit that I don't have a perfect understanding of this, and going directly to the source, such as some of Stephen Hawking's writings and some of his math behind it, might be more helpful for some people. The next thing that Stephen Hawking mentions is that emissions of even some of the highest emitting black holes are going to be really hard to detect, even if the black hole were as close to us as Pluto. I also love a sentence that Hawking wrote regarding black holes from our early universe. He says that, quote, "If we do find one, I will get the Nobel Prize," unquote. This man had a confidence in his life's work, and I aspire to this level of confidence in myself. Predicting black hole radiation could only be done using the combination of both general relativity and quantum mechanics. It was the first of several big predictions that used both. Initially, those theories about predicting black hole radiation received a lot of backlash because they suggested that black holes actually did release something, even if that something was very small. Lecture number 5 opens with an anecdote about Stephen Hawking visiting the Vatican in the 1970s. This was during a time when the Catholic Church was openly embracing modern science, determined to avoid repeating their infamous treatment of some scientists like Galileo. For a quick refresher, Galileo was an Italian scientist charged with heresy in 1633 for advocating that the earth revolved around the sun. Luckily, he pled guilty for a lighter sentence and received only house arrest until he died 9 years later. So, when Hawking was visiting the Vatican, the Pope gathered a private audience of scientists and told them that they could study everything after the Big Bang, but the Big Bang itself was, quote, the moment of creation and therefore the work of God, unquote. Hawking goes on to joke about how glad he was that the Pope hadn't heard his talk a few minutes prior, which was about that very topic. Okay, so next in this chapter, Hawking goes on to talk about the generally accepted hot Big Bang model. As the name implies, it starts off really hot at the very beginning, at a single point in space. As the universe expands, the temperature of matter decreases. As matter and the space around it cools, the particles start moving slower, meaning that particles in the gases start clumping closer together because the particles are no longer flying past each other at high speeds. Around 25% of protons and neutrons are converted to helium during this time, while the rest of neutrons simply decayed into protons, also known as hydrogen atoms. A note for myself here is that I actually thought all atoms had an approximate equal number of protons and neutrons, but a quick Google search tells me that hydrogen is the exception, where hydrogen has 0 neutrons and a single proton. So I must have forgotten this from my chemistry days, and I apologize to all my chem teachers along the way. Going back to the accepted Big Bang model, some of the radiation left over from the hot early stages would have cooled to a few degrees above absolute zero, but that temperature would still be observable today. That observable temperature is confirmed by a whole other topic that I'm not going to go into detail about, called the cosmic microwave background radiation, CMBR. Therefore, researchers like Hawking are generally happy that they have the right picture when moving backwards from our current time until they reach about 1 second after the Big Bang. During the expansion and cooling phase, some areas would have slightly more mass than others, resulting in a slightly higher density. So gravity would have started pulling matter towards the center of those regions. In many of those cases, the centers of those regions start rotating, which pulls the matter and it's kind of swirl around it. Kind of like if you were looking at a hurricane from above, like if you were looking at the way a hurricane is swirling from a satellite imagery. As more matter is pulled in, these centers of those regions spin faster until the edges are spinning fast enough to actually resist the pull of gravity inwards. Then they continue spinning at that speed. And this ultimately results in disk-like galaxies. The Milky Way, for example, is one of those galaxies. Hawking next talks about how this process results in stars forming, which I know we touched on in an earlier lecture, so I'm going to keep this as brief as I can and probably repeat myself a little bit. As those galaxies are spinning, they can sometimes break off into smaller clouds of matter and collapse under their own gravity, where the temperature increases until it gets hot enough for nuclear reactions, which in this case is fusing hydrogen into helium. Energy gets released as heat and light, while the additional heat also increases pressure, which continues until it balances the gravitational attraction and momentarily stops that gas's collapse. As we discussed earlier, more massive stars collapse faster and use up hydrogen faster, which means that they also convert helium to larger elements like carbon and oxygen, eventually collapsing to either neutron stars or black holes. Outer regions of these galaxies may blow apart in a very bright process called a supernova, which releases a bunch of heavy elements for reuse in different stars and rocks. Around 5 billion years ago, a star broke apart, some of whose heavier elements were used to help form a large star at the center of what is now our solar system, which of course we call the sun. Even more exciting, a small amount of the heavier elements stuck around to form planets in our solar system, including the Earth. Okay, I got a little sidetracked there, so we're going back to the Big Bang process. The original hot Big Bang model would have worked only if the universe had really even densities in every direction. The original hot Big Bang model would have worked only if the universe had very even densities in every direction. A researcher named Alan Guth from MIT proposed a slightly different beginning, in which the density of matter did not have to be perfectly the same in every direction, which ultimately made this theory more palatable to most scientists and easier to believe. Guth proposed that the early universe had a period of very rapid expansion, which he called inflation. Any irregularities in the original densities of a singularity would be smoothed out by this rapid expansion, resulting in similar densities across our universe, similar to smoothing out wrinkles in a balloon when somebody blows it up. Stephen Hawking and some others spent years in the 70s and early 80s trying to work out exactly how the period of rapid inflation could have come to an end. Because as we discussed earlier, we can estimate the universe's current expansion rate and know that it's much slower than what inflation would have suggested. Lastly, I'm going to talk about quantum gravity for a minute, which is a topic that Stephen Hawking and some others continued working on for a number of years. Quantum theories came about because Hawking and others needed laws that worked for both now and also at the beginning of time. As we mentioned earlier, classic general relativity is going to break down at singularities. So those are going to be black holes and the Big Bang. In other words, we needed some theories that fit both the singularities and also modern times. Quantum theories hold up everywhere, including at the beginning of time. Even as of today, the scientific community doesn't have a great way to combine both quantum mechanics and normal gravity. However, scientists are confident enough in certain aspects of what that unified theory should be that we can discuss some possibilities and probabilities of that unified theory existing. Quick side note for myself is that we are starting to get into some kind of fuzzy territory here by trying to explain things without using any math, much of which I will freely admit to not 100% understanding myself. And I think that's okay. We can't all know everything, so sometimes we need to rely on experts. For the sake of this episode, I'm going to consider Stephen Hawking's statements as true, as he's certainly an expert in his field. All right, back to the text. In quantum theories, a particle going from point A to point B does not have just a single history. Instead, it has a bunch of potential paths going from point A to point B, which it follows in something called imaginary time. Basically, we can add up all of those imaginary paths to determine the most likely probabilities of those paths that the particles can take. The distinction between space and time kind of disappears in this approach, which allows us to work with, quote, imaginary time. At least in the mathematical sense, we're able to get a probable history of the way that things are happening. Using quantum theory here, space-time is shown to possibly be finite in extent, but without any singularities forming boundaries or edges. In other words, there's no boundary or edge to how far out space goes. Finding it kind of hard to wrap my head around this, but overall, I'm imagining empty space just kind of going on forever is the first thing in my mind. And the second thing is that we throw a bunch of stuff into that empty space, but it only goes out so far. So if we have empty space going out forever, we throw a bunch of stuff kind of in a circle in the middle of that. And if we look at the furthest away star ever created, there's just going to be more empty space beyond that forever. That is going to be the end of lecture number 5. Thank you all for listening. I hope you enjoyed this and learned something fun. Take care.